Okay, from last class, we discussed about queuing theory. Queuing theory is very important concept when you try to analyze service system or manufacturing system under uncertainties. Okay. I explained about basic queuing model. So there are many types of queuing models, but we are going to focus on the simplest one. Single server, single stage system. And then I demonstrate a very simple example with the data, and then how to calculate performance measures like average waiting time, average number of customers in the queue or in the system using some basic formula. Now I'd like to introduce how to examine such a system under assumption called steady state. Okay, steady state is very important concept. When you try to examine such system under uncertainties, we first need to check whether this uncertainty can be defined, which is independent of time t. Okay, so mean variance or name of the distribution for random variables related to the system cannot change as time goes on. If it can change, they can change, some of them can change, then we cannot just apply such a concept. So steady state is very strong assumption. Sometimes the system satisfies such condition, but sometimes, other times, we first need to check with the data. Okay, and then as long as the system satisfies with such assumption called steady state, then we have a chance. Not sure yet, but for the specific case like queuing system, we need further assumptions like interarrival times follows exponential distribution, and service times are also follows exponential distribution and independent. Okay. Now we are going to consider these two very strong assumptions. Okay. First one, steady state. Okay. Second one, in the simplest queuing system, single server, single queue system, uncertainties are from two factors. First one, arrival process, and second one, service part. Okay, so we can define such randomness with distribution of interarrival times and distribution of service times. Okay, they are all uncertainties we are considering in the system. The system means single server, single queue queuing system. Okay, and we can define, since we have an assumption that these times, interarrival times follow exponential distribution, and the service times exponentially distributed. So all we need is parameter values. Okay, exponential distribution has a single parameter, right? We call this late. Okay, interarrival time exponentially distributed with parameter lambda. We call this arrival late lambda. Okay, and then service time, similarly, service times exponentially distributed with late mu. We call this service late. Okay, since we have an assumption exponentially distributed, later we can think about different cases. Okay, even though these service times or arrival times are not exponentially distributed, we can define such rate. Okay, arrival late and service late, but in this course, we can think about exponential case first. Okay. Anyway, this rate is about the measure of the speed, how fast this arrival event occurs. Okay, interarrival, I mean subsequent events arrivals, how fast. And then we can represent this rate with different unit, like time. Okay, we call this mean inter-arrival time. And when you consider exponential distribution, okay, exponential distribution, and like Poisson process, okay, this mean inter-arrival time is exactly the same as 1 over arrival rate. Okay, so we assume that this system is steady state, even though we consider uncertainty steady state and arrival process connected to some exponential distributed, and service times also related to exponential distributed, and rate represents speed of the event occurs. Okay, and time is inter occurring time between two subsequent events. Okay, here is an example. 6 customers visit the store during an hour on average when you consider the data. Okay, then average rate, arrival rate would be 6 customers per hour. So you can observe the system, right, with the data. And based on unit, you can define arrival rate. And also you can define the same information with different units, like 1 over 6 hour per customer. They represent the same meaning, right? How fast this event occurs, right? But if we consider different unit rather than hour, if we use minute, then there is the same as 10 minutes per customer on average. Okay, average inter-arrival time is 10 minutes or 1 over 6 hour. So since we discussed Poisson process, I think you are familiar with such concept, right? But we can apply the similar concept to the service area. Okay, service area. So we can think about a cashier. Okay, checkout counter of the market. Okay. So this is kind of capability of this server. How fast they can handle the jobs. Sometimes servers, sometimes it can be a machine in the manufacturing system. Okay. Anyway, we can express the speed of how fast they can handle the jobs. Okay, with the service rate, like on average 5 customers in an hour, cashier can handle such number of customers. That means service rate is 5 customers per hour, and we can represent the same information with different units, like 1 over 5 hour per customer. So on average, he or she, cashier need like 12 minutes to handle a customer on average. Okay, so we can represent the same information with different unit, rate or mean inter-occurring time. When you consider arrival process and the service area, these two information is very, very important. So even though you don't have any information, okay, you don't have any information like distribution information or steady state or not, when you try to examine the system, if you consider this system as a queuing system and you want to examine how fast you can manufacture a product, okay, that's the closely connected to your profit when you try to operate the system or cost. Okay, then the first step is you need to figure out such information. Okay, with the more precise information like distribution information and steady state or not, then you can examine the exact number like average number of customers in the system per unit time and so on using stochastic process concepts. Okay, But before you consider such mathematical or analytical results, okay, at a glance, when you see the system, you have just 1 second to determine this, some decision. Okay. Okay. Very simple problem. So then, if the system is like considered as queuing system, then first you need to think about these two information: arrival rate and service rate. Very important. Here is a very simple example. So 10 customers arriving to the system per hour on average, okay? And we can handle 20 customers per hour. What happened? How many customers we can handle in an hour on average? 10, right? 10. How about the bottom case? 10. Yes. This speed of the speed of arrival process is faster than speed of service process. Okay. What happened? This waiting line gets longer and longer, and this how many customer can be handled in a unit time can be determined by service rate mu. Okay, very important concept. We can expect two different this based on the information, just two information. We can come up with some very important results. In this case, maybe waiting line might be shorter, and server might be very compared with bottom case, server how busy server is. When we consider how busy server is, then I think 50% of time he or she is busy, and rest of time I think the server is idle. Okay. Bottom case, server needs to working on and on and on and on and on. Okay. On and on. And then this speed of we call this throughput. Okay. Throughput. How many customer can be handled in a unit time? This is a very important measure. Okay. Throughput. Throughput can be determined by the service rate. And in a manager's point of view, you lose a chance to handle more and more customers, right? If you once you handle a customer, you can earn money, right? Like let's say 10,000 won, okay? Then as long as you can handle more and more customers per unit time, then you can earn more and more money, right? So you can think about that. Two factors when you design a service system or manufacturing system. The thing is, this value is deterministic. Then you can find exact number. You when you try to earn as much money as possible, okay? Then we can get exact number, okay? We can get exact number, but the problem is variability. This arrival process has the randomness, and the service service rate is based on the randomness, right? There exists some variability. Okay, based on the variability, the problem is more and more complicated to analyze the system. But at a glance, first time you need to figure out two information and how fast we can handle the customers or parts, or how fast we can make some products in a unit time. Okay, based on the such information, you can determine. So one of the important concept is traffic intensity. So when you figure out two informations like arrival rate and service rate, then we can examine whether the system is stable or not. Stable means we can handle current customers. So we don't have to consider large amount of space, okay, large space to handle some waiting customers. Okay, we call this stable system. Okay, stable system. But unstable system, in an unstable system, someone needs to wait long time. And if we want to handle all the customers, then we need large space, waiting area. Okay, because this speed of service process is slower than arrival process, speed of the arrival process. We call this unstable system. When you calculate the proportion between lambda, arrival rate, and mu, service rate, then we can determine whether the system is stable or not. Okay, is this we usually use rho as a proportion of lambda and mu. Lambda over mu can be defined by rho. We call this traffic intensity. If traffic intensity is less than 1, then we call this system stable system. Other than that, we call this system unstable system, and we need to do something. We need to do something. We expect some bottleneck, large amount of parts in front of the machine, or many patients in front of the doctor's office. Okay, that's all about unstable system. We can examine the system in a server's point of view, how busy he or she is. Okay, we call this utilization. We are going to use similar measure, low, but this utilization cannot be greater than 1. 120%, it is not possible. Okay, even though you are working 24 hours. Okay. So this law is less than or equal to 1, and actually this is a proportion of time that server is working out of total amount of time. Okay, so how busy the server is. Usually this utilization is greater than 0.8, 0.9. In practice, that's the maximum value. Okay, that's the maximum value. Because 100% is like impossible, not realistic. Okay, 80, 90% is busy enough. Okay, when you try to examine the system, then maybe, unless you spend more money, the server will quit. Okay, too tired. Based on the 100% utilization, it is impossible. Even though you consider machine, you can think about breakdown for the machine. Okay, 24/7, working, then breakdown. So this is very important measure when you try to understand server's point of view. And throughput. This is kind of manager's point of view. How fast we can make a product, how fast we can handle the patients in the hospital, customers in the market, and so on. It is directly connected to your profit or cost. Okay, this number is very important measure. So throughput, as we can see the figure. This is based on the how fast we can handle the service area relative to the arrival process, speed of the arrival process. As long as this traffic intensity is less than 1, then this throughput is directly the same as arrival speed of the arrival process, since we can handle all the customers, okay, with the system. But if the system is unstable, then this throughput is the same as service rate. And in that case, we can consider some events like customer will leave because he or she needs to wait long time. So you can lose the customers, or you can lose the chance to sell products, okay, in a manufacturing system. So I would like to mention how specify the type of the queuing system is first, okay. Actually, we have some way to determine type of the queuing system with some information, 5 different informations. We can characterize this single server, single queue, okay, and then we can name the type of the system. Actually, this type can be determined by information of population of the customer in front arrival, based on the arrival process, and service area information, like how fast server can handle, and then waiting area. So this is the rule. Basically, we need information, 5 different informations. This slash T slash X slash C slash K slash P. Okay. But this former 3 parts is the most important part. Okay. So first symbol T represent distribution type of inter-arrival process. Okay. Inter-arrival times. Distribution type of inter-arrival times. If inter-arrival time follows exponential distribution, then we can mark AM. Sorry, M. M means inter-arrival time follows exponential distribution. Okay. And next character X represent service time, distribution type of the service times. Okay. If service time follows exponential distribution, we can mark M. Okay. For these 2 characters, okay, M represent exponential random variable, G represent general random variable other than exponential, and then D represent deterministic number like constant. Okay, constant. So T and X in the this first place and the second place, you can mark one of them D, G, M. Okay, and the first place character in the first place represent the distribution type of the inter-arrival time, and second one represents distribution type of service times. So when you try to calculate some exact numbers as long run average values later, we are going to use MM something queuing system. That means inter-arrival times follows exponential distribution and service times follows exponential distribution. Then you can apply continuous time Markov chain concepts. Okay, continuous time Markov chain. And then C represent number of identical and parallel servers. Okay, like call center problem. We consider 2 different cases. First one, identical to servers, right? We don't have to discriminate 2 different servers. They are the same. But second case, we discriminate 2 different servers like John and Mary, right? But we are considering the first case. Okay, if they are identical means service rate are the same for all the servers. Okay, and they are independent. Then we can just put the number of the servers in the middle of this notation. And then we can add two more information. K represent system capacity. How many customer can be surgeon in the system? How many parts can surgeon in the system, can stay in the system? There exists some capacity, like in front of the doctor's office. Okay, there is a waiting area, but we don't expect like 1,000 patients in front can exist in front of can wait before seeing a doctor, right? So there exists, in practice, there exists capacity. So we can put the number. So for C, K, P, we can put the numbers. Just a single number or infinite. Okay. If we don't consider any such information, then we can just put infinite. Otherwise, we can put the number. P represents size of the population. If we consider the system for any any customers not precise, cannot be precise, then just general customers can be formulated as just infinite population. Okay. So here is some more information you can read. Examples. So when you try to examine the queuing system, you need to figure out steady state or not first. Okay, and then steady state. Then you need to figure out stable or not. If it is stable, then you have a chance to calculate some very important measures like utilization, probabilities, long-run average values. Okay, especially for something queuing system. So and then you need to categorize the system. Like there are two workers who are responsible for 10 milling machines. This one is very difficult one. Let's consider simpler one first. This example. Single chair, hair styling shop. Okay. Inter-arrival times. Exponential distribute with rate 2. Okay. A half hour per customer mean value as a mean value. Service times exponential distribute mean a third hour per customer, and then we don't have to consider waiting space, and this service system is for anyone, any customer. Okay, so how can we specify the type of the system? First, distribution of the interval time follows exponential. So we can put character. So what type of the queuing system do we consider? M, right? M. And service time follows exponential distribution. M. How many server? Identical and parallel server there exist? One, right? Just one server. And we assume the system capacity is infinite, and this system for any general customers. So infinite. That's the type of the queuing system for this case. Okay. How about this case? Patients arrive to the hospital. Arrival process is Poisson process. Service times, we have two identical, C number of, any general C number of identical doctors, okay? Doctors. You can think about multiple doctors, okay? But these doctors can be considered as identical and parallel servers. Then this one, and service times follows exponential distribution. Then this one follows MM, and if C number of doctors there exist in the system, then MMC, infinite system. Okay. So we can think about many different cases. So first one is how to specify the type of the system. Okay. So let's consider MM1 system first. MM1 system first. Okay. As we discussed earlier, as long as inter-arrival time follows exponential distribution and service times follows exponential distribution, then we can calculate the numbers. Okay, we can calculate the numbers. What kind of number we are interested in is performance measure based on infinity. Long run average number of customers in the system. We usually use L. Okay, this is L. L is limit time t goes to infinity 1 over t 0 to t L of t dt. We can integrate this L of t for the system and then divided by t. If this t goes to infinity, what happened? Based on this number, large L, you can think about how many customers in the system we can see when you visit the system. Okay. So this number is large. That means probably you need to wait long time. Okay, indirectly. And W, waiting time. Okay. This one, as we discussed before, as time goes to infinity, the 1 over number of customers handled by servers until t. Let's say this one is m. And we can think about just waiting line. So L of Q is limit t goes to infinity 1 over t. If we consider just the number of customers in the waiting line, not just the system, then we can calculate such number. WQ similarly limit t goes to infinity 1 over m and summation for all customers waiting time. Okay, let's say this large t goes to infinity is the same as large m goes to infinity. We want to calculate such information. Okay, and this reduced law is very important concept. As long as the system is stable, then we can calculate the reduced law based on the numbers, how fast we can handle these customers, or how fast we can make the product. Okay, this one can be marked by lambda in this case. When you calculate L and W, then this how fast we can handle the customer is actually the same as L over W. in front of, even though we consider we want to operate the system long time, okay, long time, we can examine the number. This is very important concept, especially for steady state, under the steady state condition. We want to calculate such information for a certain type of system. Okay. In this case, I mean, this Riddle's law, L equals lambda times W. This one is different from arrival rate. This one represents throughput. So I'll change notation. This is Con method is about how to compute stationary distribution of a CTMC. So far, how can you do it? How can you do calculating stationary distribution of the CTMC? Do you remember? Pi times Q equals 0, and summation of pi I 1. Okay, when you solve the system of linear equation, then you can find the stationary distribution. But we have a different way. Okay, we have a different way. I think you are familiar with this method because this structure is exactly the same as the structure we discussed in the DTMC, except we are going to use rate information rather than probability information. Okay. Actually, to consider Con method, you need to draw rate diagram first. Okay. First step, draw rate diagram. Second step, for each node J, in this case J, node represents the state, right? Each state J. Okay. You can construct balance equation. So outflow left hand side and inflow right hand side. Okay. Outflow is summation of pi j times rate from state J, lambda jk for any k connected from the state J. And right hand side, summation of pi k destination node k, pi k times lambda kj, no, origin node, okay, and from the k node k, this flow from the k to the j for the fixed j. Okay, so we can construct all the balance equation for each state, and then when you solve this system of linear equation under one more condition, summation of pi j is 1, then you can get the exactly same answer as solving this pi q equals 0 and the summation of pi I equals 1. Sorry. Okay. Let's think about the example.